We'll be continuing in Chapter 3 today, talking more about polynomial functions. And specifically, we're going to be looking at the qualities of polynomial functions and then their graphs. And this will be part 1 because there is a lot to cover in this lesson. So the main objectives we're doing 3.1 or 3.2 part 1 are to identify polynomial functions, recognize the characteristics of the graphs, determine end behavior, use factoring to find zeros, and the other things we will do in part 2. So here's a definition, and I know there's a lot of letters there, so just bear with me here. The n is a non-negative integer. So you notice the n is the exponent. And then they're real numbers, and we're not going to be using a 0 as that leading coefficient out front. So this n minus 1, so just think about it. If this was a 4 for n, then this would be 4 minus 1, which would give you a 3. And then you could keep going, and then you would have the squared term, then the x term, and then no x at the end. So you always go from the highest exponent down to the lowest exponent. And the number a sub n there, the coefficient of the variable to the highest power is called the leading coefficient. So this has the highest exponent of a 4. And then you look at the number out front, and that is the leading coefficient. So here's just some examples of what's polynomial and what's not polynomial. So we'll start with the polynomial functions. So this one is degree 5 because that is the highest exponent we have. This one down here is a degree of 6. And you can see they did the factoring, they did the FOIL to get this, and then they went ahead and did distributive again, and you ended up with a 6 as the highest exponent, so it's a degree 6. Now these non-polynomials, you'll notice that the exponents are ones that aren't allowed for polynomials. So square root of x is the same as x to the 1/2. That is not an integer, so that's why it's not polynomial. And then if you have the x squared on the bottom of a fraction, that means negative exponents. And we said the exponent can't be negative. So if it's negative, then that's not allowed either. Okay, and then I have this note at the bottom. So a constant function, if it's just f of x equals a number that's not 0, it is a polynomial function of degree 0. So that would be, let's say I have f of x equals 4. There's no letter on it, but you could technically say that's 4 times x to the 0, meaning there's 0 x's. So that's why it's degree 0. That is the same as just saying 4, because I have no x's. If it's linear, then you have an invisible 1 there. So that is a degree of 1. A quadratic, are the ones we've been talking about a lot, are squared. So it's a degree of 2. So in this lesson, we're going to focus on polynomial functions that are a degree 3 or higher. Okay, now we're going to talk about what the graphs are going to look like. So polynomial functions of degree 2 or higher have graphs that are going to be smooth and continuous. So by smooth, we mean that the graph contains only rounded curves, there's no sharp corners. By continuous, we mean that the graphs have no breaks or gaps and can be drawn without lifting your pencil. So the first two are examples of polynomial functions. You can see they're smooth, there's rounded curves, there's no sharp corners, and there's no gaps or breaks. Then the not graphs of polynomial functions, this one there's a break in the graph, so it's not polynomial. This one has a sharp corner, so that's not going to be polynomial either. Okay, now we're going to talk about the end behavior. So like what's going to happen with the arrows at the end. So the behavior of the graph of a function to the far left or the far right is called its end behavior. So where do the arrows go on the left and where does the arrow end up going on the right? So although the graph of a polynomial function may have intervals where it increases or decreases, the graph will eventually rise or fall without bound or without end as it moves far to the left or far to the right. So the main thing we're looking at is the sign of the leading coefficient, which we said was a with an n subscript, and the degree n of the polynomial function reveal its end behavior. So we're going to be talking about the leading coefficient test to see what's going to end up happening to the graph. So as x increases or decreases without bound, the graph of the polynomial function will eventually rise or fall. So I would definitely recommend printing out these notes because this just takes a while to look at, to study, to review. So the leading coefficient test. So first you're going to look for the n. That is the highest exponent. If that n is odd, so let's say it's x to the fifth, for example, that is an odd exponent. Then you need to look if the leading coefficient is positive, the graph falls to the left and rises to the right. So let's say maybe it was 2x to the fifth. That's going to go with this one. If the leading coefficient is negative, the graph rises to the left and ends up falling to the right. So let's use our x to the fifth again, but this time it's going to be a negative coefficient, so let's do -3, for example. That will match with this. Okay, now if the n is even, so let's use x to the fourth for this one. If the leading coefficient is positive, the graph rises to the left and to the right. So it's a double rise if it's positive. So let's pick 2 for that. If the leading coefficient is negative, the graph falls left and right. So that makes sense. If it's negative, it's going to be going downward. So maybe -3x to the fourth. So that one's not too hard to remember. The odd one is, you can think of it as it's an odd looking graph because it falls on one end, rises to the other end. It's just, I would just try to think of some easy ways to remember these. I think the even one is easier. Positive means it's going to go upward, negative means it's going to go downward when you look at that leading coefficient. So let's go ahead and try this. It says use the leading coefficient test to determine what's going to happen at the end of this graph. So we have x to the fourth minus 4x squared. So we look at the highest degree. This is our n. It is 4, which is even. So if you remember from that previous slide, the even ones are either going to rise on both ends or fall on both ends. So they have the same behavior. They're either going to rise on both sides or fall on both sides. So now you look at the leading coefficient, which is just a number 1 if there's nothing out there. It is positive, so it's going to rise to the left and to the right. And this is what the graph ends up looking like. You could always go to Desmos. I think that's a really good resource just to check to see what does this graph end up looking like. Just to double check your answer. It will graph these for you and show you what the graph is going to look like. So it's a pretty cool website where you can use a online graphing calculator. But you cannot use that on a test, so don't get used to utilizing that too much. Okay, let's look at this one. So now our highest exponent, and notice you have to put the exponents from highest to lowest. So it's a 3, which is odd. So odd functions are going to have a rise and a fall. Opposite behavior. So the leading coefficient is a 1 again, which is positive. And then if you look back at that picture from a couple slides ago, the graph is going to fall on the left and rise to the right. So it ends up looking like this picture off to the right. There's a fall on the left, and then it ends up rising on the right. Okay, let's go ahead and try this one. Use the leading coefficient test to determine the end behavior of this graph. So there's two ways you could do it. We could multiply it out, and that can help us find our exponents. So I'm going to show you that method. So x minus 1 squared is going to be x minus 1 times x minus 1. Then we have x plus 5. So let's just do one thing at a time here. So we have negative 4x to the third on the outside. Then we're going to get x squared minus 1x minus another 1x plus 1 times x plus 5. And maybe you remember your perfect square rules. You're going to notice I have a negative 1x and another negative 1x. I'm going to change that to negative 2x. Okay, now I can go ahead and apply multiplying this one out. So x squared times x is x to the third. X squared times 5 is positive 5x. And don't forget about this negative 4x to the third out front. Then I'm going to have negative 2x times x is negative 2x squared. And sorry, this should have been 5x squared because I multiplied it by an x squared. Then I have negative 2x times positive 5 would be negative 10x. And then I have 1 times x and 1 times 5. And now all of that needs to be multiplied by my negative 4x to the third. So I'm going to keep drawing my arrows. I won't draw them all, but when you multiply exponents here, you actually end up adding. So I have 6 x's there. Then I have, and actually let's go ahead and combine these. So that is going to be 3x squared. So if I take that times my negative 4, I get negative 12x to the fifth. I can also combine these to make 9x negative. So if I multiply that by my negative 4x cubed, I get positive 36x to the fourth. Then I have 5 at the end that I need to multiply by negative 4x to the third. Okay, so you can see here this takes a while, so we're going to want to learn a shortcut, but I wanted to show you where the shortcut comes from. So now we notice this 6 is even, and then the leading coefficient is negative 4. So a negative leading coefficient. Okay, so if you remember the even graphs, they're going to either rise on both ends or fall on both ends. Since it's negative, we're going to fall on both ends of the graph. Okay, option 2 is going to be a lot faster. So when multiplying exponential expressions with the same base, you can add the exponents. So if I look here, I'm going to end up, if you look at this, I'm going to be multiplying that negative 4x to the third eventually by an x squared, and eventually by just an x to the first, which you can see in my work in option 1. So if you just add these up, I'm going to end up with an x to the 6th eventually. So that's the shortcut trick. Just add up your x and your exponents, what you're going to end up getting, and we still get the same thing that we had over here, so it's even. And we know that that negative 4 is going to be multiplied out front of everything, which matched over here. So that's going to be the shortcut, but I did want to show you how you end up getting that. Okay, so here is what the graph ended up looking like, and we said that the degree is a 6, which is even, and it's either going to rise or fall on both ends. So the leading coefficient we said was negative 4, which was negative, so you can see that it falls on both ends. Okay, here's an application problem. So use end behavior to explain why the equation below for AIDS diagnosis is only appropriate for a limited time period. So if we look at this, we have the highest exponent is a 3, which is odd. And we said odd degree functions have graphs that both rise and fall. And our negative 49 is the leading coefficient, which is negative. If you look back at that chart we had, this would mean that the graph rises to the left and doesn't really matter what it does in between. We know that it's eventually going to fall to the right. So eventually, if I had my x and y axis, it's eventually going to fall into the negatives. It's going to be impossible to have a negative amount of AIDS cases, so that's why we would have to stop somewhere before we got to the negative. So you'd have to figure out the amount of time and when that would be, and then from then on, the graph doesn't apply anymore. Okay, we're going to end by talking about the zeros of polynomial functions, which is a big part of your next test, so make sure you study this. If f is a polynomial function, then the values of x for which f of x is equal to 0 are called the zeros of f. These values of x are the roots or solutions of the equation. So when f of x, if we set that equal to 0, we'll find the roots. Each real root appears as an x-intercept of the graph. So we're going to start by finding all the zeros of this equation, x to the third plus 3x squared minus x minus 3. So we find the zeros of f by setting f of x equal to 0. So here's my original equation. And it says to set that entire quantity here equal to 0. And our goal is to figure out what the x's would be. Okay, so we're going to factor by grouping here, so we can look at this pair and then this pair separate. So in the first pair, we could pull out an x squared, which would leave us with an x and a plus 3. The next pair, we're going to pull out a negative 1, so that we're left with an x plus 3 also, because those should match with this one. So that means I have x squared minus 1 as one of my binomials, and then x plus 3 is the other one. Okay, and we want to know what will make this equation equal 0. So I'm going to solve for x squared minus 1 equals 0. Do that over here. And then x plus 3 equals 0. So if you solve that, if I add 1, I get x squared equals 1. Take the square root. So x could be positive or negative 1. And this one, if I subtract 3, I get x equals negative 3. Okay, so what that means is those are the x-intercepts. So if we think of a graph, I'm going to say it's going to hit at positive 1 and negative 1, and then negative 3. So those coordinates, this one would be negative 3 comma 0. Then over the other two, we would have a negative 1 comma 0 and a positive 1 comma 0. So this one has 3 zeros. Okay, and so this just reiterates that. I just wrote it out again in case we ran out of room on the last one. So these were the zeros, those are x-intercepts. So these are the coordinates that the graph is going to pass through. Okay, now this one I have laid out for you. So we find the zeros by replacing f of x with 0. So they start by pulling out an x squared from this pair. Then they pulled out a negative 4 from this pair. So I'm getting x plus 2 times x squared minus 4. So the first one you have to solve is x plus 2 equals 0. So you get negative 2. And the other one is x squared minus 4 equals 0. So you add the 4 over. Then you take the square root. So you get x equals positive or negative square root of 4, which is just positive or negative 2. Okay, now on that one we had negative 2 happen twice, so you only need to list it one time. So it's going to end up touching at negative 2, 0, and it ends up passing through completely at 2, 0, which we'll talk about more when we talk about how to finish the entire graphs. But for now, you just need to know what these x-intercepts are going to be. Okay, we will end with this example. So this one has a negative out front, so you need to be a little careful. We're going to start by replacing this with 0. So to make this look like something we've seen before, we're going to multiply everything by negative 1 on both sides, which still gives us 0 over here. So as long as you do it to both sides, it does not change the equality of the equation. So now we turn this into a positive because a negative times a negative is a positive. This turns into a negative 4x to the third. This turns into a positive 4x squared. Then we can go ahead and factor that. So out of all of that, we can pull out an x squared to start, which leaves us with x squared minus 4 and 1x left, plus positive 4. And if you remember your perfect square rules, this is going to factor into an x minus 2 squared. So now our two equations, I'm going to have just x squared equals 0 and x minus 2 squared equals 0. So I'll go ahead and solve those. This is just taking the square root of 0, which is just 0. You can't have a positive and a negative 0, it's just 0. This one, if you take the square root, you end up with just x minus 2 on this side, and we have 0. Add the 2, and you get x equals 2. Okay, so as coordinates, we would end up with 0, 0, so the origin, and then 2, 0 is the other x-intercept. Okay, so that is the end of part 1, and we will talk about the other objectives in part 2.